So what we want to talk about first today is we want to talk about the integration formulas and the net change theorem. This is a relatively small little theorem, and it gives us a way of thinking about how one aspect changes as another aspect changes in application problems. The first thing we want to do is work through a few integrals using the fundamental theorem of calculus, and that way kind of review you a little bit on what we talked about previously and get you warmed up, and then we'll look at the net change theorem. So the first thing we want to do in section 5.4 is talk about these basic formulas that we have that are for the integration. Now, I've given you these basic integrals before on a previous slide when we were looking at a different section, but here are the basic integration tables. Now, these are the ones that you're going to encounter the most often in this class. It's basically going to be the integral using of a constant, which of course invokes the power rule, which gives you kx, and then the power rule. The integral of 1 over x is natural log of x. The integral of e to the x is e to the x. And then we have the common trig integrals that you see down here. And on the side next to them, we have the derivative form that leads to the integral form. Now, at the very bottom, we have the inverse trig derivatives and integrals, which we have not talked about yet. So the inverse trig integrals are going to be coming up here at the bottom, and they come up, I believe, in section 5.7. So we have not discussed these yet. So there are tables that can be found that look at these kinds of things. And later in class, I'll show you a table called an integration table that has all the formulas that are known in common. The one that I have isn't all the known formulas, but there's books called the CRC tables that contain all the known integration tables. They used to be the most valuable books for undergraduates because they contained all the formulas, and they were extremely expensive. That's not as expensive now because you can get the integrals that you need off the internet. So those are the primary integrals that you need to remember. Let's go ahead and start with example 1. We want to find the definite integral of the function x squared minus 3x over the interval from 1 to 3. So when we're looking at this one, we want to take and find a way of integrating that function. Now, the variable that we use is a dummy variable. So again, we could use x, or we could use t, or we could use some other symbol. So to integrate over 1 to 3, we put the limits of integration as 1 to 3, and then we're going to have the function in here. So we can use x, or we could switch to another variable. In a definite integral, the variable is a dummy variable. It doesn't stay in the integral or in the answer. It disappears at the end. Now, remember to do this, you start just like you're doing an antiderivative function. You find the antiderivative of each term individually, and then we're going to evaluate it from the upper limit of integration minus evaluating it at the lower limit of integration. That's the fundamental theorem of calculus part 2. So applying the power rule on the first term gives us x to the 2 plus 1 divided by the new power, which is 3, minus 3 is the constant, x to the 1 plus 1 divided by the new power 2, all evaluated between 1 and 3. Now, the next thing that we want to do is plug in the limits of integration. You can keep the 1/3 out. Now, you have a choice. You can plug the 3 into both terms and evaluate, and then plug the 1 into both terms and evaluate and subtract the upper minus the lower. Or you can plug both 3 and 1 into the first term and then both 3 and 1 into the second term. It doesn't matter, they're equivalent, it will give you the same result. So I'm going to go ahead and plug them into each one individually. So I have 1/3, partly because I have coefficients. And this becomes x to the third. So this becomes 3 to the third minus 1 to the third minus 3/2 times, and this becomes x squared. So I get 3 squared minus 1 squared. Right? So I plug them into each in turn, and I've done the subtraction between the upper and lower limits of integration within each one. 3 cubed is 27. Then we're going to be subtracting 1, which gives us 26. So we have 26 over 3. And then the next one, we have 3 squared, which is 9, minus 1, which would give us 8. And then we have this multiplied by 3/2. So the 8 and the 2 give me a 4. So I have 26/3 minus 12. And then to get a common denominator would be 3. So I have 26/3 minus 36/3, which gives me a negative 10/3 as the final result. Right? When there are constant coefficients like the 1/3 and the 3/2, I think this is a slightly faster way of doing it than plugging the upper limit of integration into both and then plugging the lower limit of integration into both. I think it's slightly faster to be able to factor the 1/3 off. Okay. Let's take a look at the second example. This is similar to one we did yesterday when we were looking at doing integration with the Fundamental Theorem of Calculus. This one does not actually require the Fundamental Theorem of Calculus. Remember, Fundamental Theorem of Calculus part 1 is the derivative of a definite integral where the upper limit of integration involves the same variable as in the differential of the derivative. And part 2 is the definite integral, so the tie between the definite integral and the indefinite. But this is an indefinite integral, which is basically an antiderivative function. So the first thing that I would do is go ahead and rewrite the two terms in a format where it would be easier to apply the power rule. So this would become x to the negative 1/2. Remember that raising it from the denominator to the numerator changes the sign, and the square root is the 1/2 power. Now we can split the radical across addition and subtraction, but we cannot split across multiplication or division. So we're going to find the antiderivative of each term individually. So this becomes the 1/2 plus 1, which is 2/2, divided by the new power, which is 3/2, which will give us the reciprocal of that term, minus x to the negative 1/2 plus 2/2, which becomes 1/2. And then because it's an indefinite integral, we get a plus c. The plus c is that constant of integration that allows us to write it as a family of functions. All right. Okay. So the next thing that we want to do is simplify. So the dividing by 3/2 is the same as multiplying by the reciprocal, which is 2/3. So I have 2/3 x to the 3/2 minus dividing by 1/2 is the same as multiplying by the reciprocal 2/1 or 2, x to the 1/2 plus c. Now you could also rewrite it in terms of square roots. If you wanted to write it in terms of square roots, you could write it as 2/3 the square root of x cubed minus 2 square root of x plus c, whichever one of those most appeals to you. Okay. Let's take a look now at the next one, which is a definite integral. This is example 3. And when we look at example 3, we know it's a definite integral because of the limits of integration. This is going to invoke the Fundamental Theorem of Calculus part 2, where we're going to find the antiderivative function of each individual term. And then we're going to plug the limits of integration in and subtract them. So remember, when you're doing this, that you are actually undoing the derivative. That's what the integral does. So you took the derivative of something to get sine, and the derivative of cosine is negative sine. So to get a positive sine, it would have had to be a negative cosine. So we have negative cosine of x, and then the second term is a negative cosine. When we take the derivative of sine, we get cosine. So this would be minus sine of x, and this is being evaluated between 0 and pi. So when we look at this particular one, and we have our integration here, this means that I could, if I wanted, take the -1 and factor it out of the whole thing and write it as cosine of x plus sine of x. And this can make it easier to do. The other thing that you can do, what else can you do with that -1 that you've now factored out of the whole thing? How can you get rid of a negative being multiplied by the entire antiderivative? What can you do with the limits of integration? Yes, that's right. So Brittany said we could switch the limits of integration, and if we switch those limits of integration, it gets rid of the negative. So that would give us cosine of x plus sine of x evaluated between pi and 0, right? Which is a different way of thinking about it, right? Very effective technique to get rid of the negatives, very handy, something that you definitely want to keep in mind and do in the future. Because I would say that negatives are one of the biggest problems I see on definite integrals, messing up the sign. So now I'm going to plug in, because I don't have any negatives now, I'm going to plug in the 0 to both. This is one of the techniques. So I have the cosine of 0 plus the sine of 0 minus, and now I'm going to plug it into both of the others. This is going to be the cosine of pi plus the sine of pi. Now, this is one way of doing it. We did it a different way last time. Last time we plugged in the upper limit of integration and then plugged in the lower limit of integration into each one. You can still do that. There's no problem with doing it that way. All right. So you can write it either one of those ways that you see right there, the one in blue or the one in pink, right? They both work, they both make sense. So when we're doing this, whichever one you choose to do, I'm going to focus on the blue. Cosine of 0 gives me 1. The sine of 0 gives me 0 minus. The cosine of pi is a -1, and the sine of pi is still 0. So this gives me 1 minus a -1, which gives me 2. Right? Now, let's take a look at the link that I have here and see what that looks like. All right, so when we're looking at the graph, this is the graph of sine x minus cosine x. And when it says 2, what it's talking about is actually making a grid that fits on a from 0 to 1 on the y and 0 to 1 on the x. And then it looks at that and says how much area is between the curve and the x-axis. Now, right now we've got blue area above, but we have to subtract the green area that's below. So if we take this area off of this graph, what's left is 2 square units, precisely 2 square units of area. Okay. What questions do you have so far?
If we were going for total area, we just wouldn't place that subtraction sign in the middle.
That's a good question, Caleb. No. If you were going for total area, you would have to integrate using absolute value, which means based on the graph that we see right here, you would have to reflect the graph between 0 and pi over 4 and use the regular function from pi over 4 to pi. All right, so let me write out what that would look like. So let me show this is not the same problem. So for total area, we would have the integral, and where are we going? 0 to pi? From 0 to pi of the absolute value of sine x minus cosine x dx. Now, the way to get the absolute value is when it is below the axis, you multiply it by a negative. That reflects it and flips it up on top. So from 0 to pi over 4, we would multiply by a negative to get negative sine x plus cosine of x dx. And that would reflect the graph from being below the graph and would reflect it up. All right. So let me show you what that would look like. I'll do it maybe in black. So that would be negative sine x. Oops, lost my equals. And does everybody see how that flipped the graph up? In this section between 0 and pi over 4, instead of being below the axis, now it's been flipped above the axis. So we would multiply by a negative in the region where it's below the axis, and then in the region where it's above the axis or on the axis, we would go ahead and leave it as it was before, sine x minus cosine of x dx. And then we would integrate these two integrals separately, and that would give us the total area. All right. Okay. Let's now look at the net change theorem. The net change theorem looks at the integral as a rate of change. So basically it says when some quantity is changed, the new value that you get out, which is basically the f of b, is equal to the initial value, f of a, plus the integral of the rate of change of that quantity that changed. So the formula can be expressed in two ways. So what we're actually looking at is the same formula that we've had before from the Fundamental Theorem of Calculus Part 2, but solving it for f of b. So this is the new value when something gets changed. Remember, a derivative represents the change in something, a change of something with respect to something else. And because this is the derivative of some function and we're trying to find the antiderivative, then we can find this new value f of b by moving f of a to the other side and then adding it to the value of the definite integral. So this isn't really something that's totally new. It's just a different way of thinking about what we've been doing and thinking about it as a rate of change. This can be applied to things like area, distance, surface area, volume, and other applications. Now, it also applies to velocity and position. Remember that we have the change in position is called the displacement. So you can have total displacement or net displacement. So total displacement would be the total distance traveled, and net displacement would be how far you are from where you began. So remember that your net displacement may include both positive and negative values as you move both forwards and backwards. So to find net displacement, what you're going to do is integrate the velocity function over the interval and then add to that the original function or the original position. So to find the new displacement f of b, you integrate the velocity function, that's the definite integral, and then you add to it the original position, which is f of a. All right. Total distance traveled, on the other hand, is always positive, and in that case, you need to integrate the absolute value, as we saw in one of the last previous examples. So let's look now at example 4. In example 4, we are trying to find both the net displacement and the total distance traveled in meters given this function 1/2 e to the t minus 2 over the interval from 0 to 2. So the net displacement is going to be basically, if we write it out in words, net displacement is equal to where you end up minus where you started. All right. So when we're looking at this one, that's the value that we're looking for. We're looking for the net displacement. So what we want to think about first off is, what does this particular graph look like? So we have 1/2 e to the t minus 2. So you can come to Desmos or you can sketch the graph by hand. Either way, y equals 1/2 e to the x minus 2. All right, so here's the graph of the function. You can see that it is the typical exponential shape. 1/2 means it's been compressed vertically by a factor of 1/2, and the minus 2 means the whole thing has been pulled down to. So instead of passing up here through 0, 1, it's been compressed by 1/2 and then pulled down to. So compression by 1/2 would have passed it through 1/2, and then it's going to pull down 1. So it's now passing at -3/2. All right. So when we're looking at that function right there, we want to think about integrating that to find the net displacement. The net displacement is going to be equal to the integral from 0 to 2, since that's our interval, of the function 1/2 e to the t minus 2 dt. So we integrate the velocity function to find the net displacement. That's where we end up minus where we started, or f of b minus f of a. Right? So when we integrate this one, we can integrate each term by finding the antiderivative. The antiderivative of e to the u is e to the u divided by du dx. So this gives us e to the t. And then the integral antiderivative of 2 will give us 2t. And this is evaluated between 0 and 2. So now we need to evaluate between 0 and 2. So let's go ahead and plug in to each term individually and do the subtraction in each term. So I'm going to factor off the 1/2, do e to the second minus e to the 0, minus 2 factored off, times 2 minus 0. Again, when there are common factors on each term, I think it's easier to plug in directly like this and leave the factors factored out. So this gives us e squared minus 1. and this gives us -4, which if we multiply out, we get e squared minus a half minus 4, which gives us e squared minus 9/2, 1/2 e squared minus 9/2, which is about negative 0.806 meters. So it ends up that far to the negative side of where it originally started. All right. So that's the way to interpret that result. It is ending up about negative 0.8 meters to the negative side of where it originally started. That's net displacement. So we've only done half the work of this problem. The other work was to find the total distance traveled. Now, total distance traveled means that we have to do a reflection on the part of the graph that falls below the axis. So we're looking at the graph right here, and we can see that part of the graph is below the x-axis. And so we need to reflect that part of the graph above the x-axis. But the first thing is we have to figure out what this value of x is here, where it crosses the x-axis. So we need to know when it crosses the x-axis. So to find total distance, we first need to find the x-intercept. So this is total distance. And we need to first find the x-intercept. Where does it cross the axis? What splits it, the graph, between below and above? Well, that basically means that the function value is equal to 0, which implies that 1/2 e to the x minus 2 is equal to 0. Or I guess we were using t, so I should use t. All right, so 1/2 e to the t minus 2 equals 0. Move the 2 to the other side. So you get 1/2 e to the t equals 2. This is college algebra work with logarithms and exponentials, but it may have been a while, or maybe you don't remember this. Then you multiply both sides by 2. So you get e to the t equals 4. After isolating the exponential, you want to switch forms so that you can get your hands on the t, or you can think about taking the natural log of both sides like we did in implicit differentiation. Remember that? Take the natural log of both sides to get your hands on the power. So the natural log of e to the t is, of course, just t. So the natural log of e to the t, let me scroll up so we can see a little clearer, becomes t, and this remains the natural log of 4. So the natural log of 4 is where it hits that axis. So let's come over to the graph and let's plot the point natural log of 4, 0. Okay, does everybody see that it's right there on the axis? So that's the natural log 4. Now, what we want to do is we want to reflect this part of the graph that is below the axis. So to reflect the graph, what we need to do is multiply each part by a negative. So what we want is to have y equal negative 1/2 e to the x plus 2. But we only want this to be on the section between 0 and the natural log of 4. Right? So now you can see that I'm reflecting with this green. I don't like the green. Let's make it black so it shows up a little better. Now you can see with this black section right here, I'm reflecting just this part of the graph up. Right? And this will give me total displacement, all right, like total area. So now what I want to do is I want to come over here and I want to write that out in terms of integrals. So I have the integral from 0 to the natural log of 4 of negative 1/2 e to the t plus 2 dt plus the integral from the natural log of 4 up to 2 of 1/2 e to the t minus 2 dt. And this will give me total displacement. Right? So then we integrate each integral separately. So take a moment and let's write out what the antiderivatives are. Note that these cannot be done together because the limits of integration are different. When the limits of integration are different values, they cannot be done in a combined form. All right. Oops, looks like I'm out of space. Okay. So working from there, we're going to have the minus 1/2 e to the natural log of 4 minus e to the 0 plus 2 times natural log of 4 minus 0 plus 1/2 e to the 2 minus e to the natural log of 4 minus 2 times 2 minus the natural log of 4. All right, and now we are going to go ahead and multiply that out and combine like terms. So e to the natural log of 4, remember from college algebra that exponentials and logarithms, natural logs are inverse operations. As long as there's no number between them in front of the natural log, they are inverse operations and undo each other. So we just get 4. So this gives me minus 1/2 times 4 minus 1, which is 3, which gives me a minus 3/2. Then in the second term, I end up with 2 natural log of 4. In the third term, I end up with 1/2 e squared minus 1/2 times 4. The e to the natural log of 4, again, like the first one, becomes 4. And then I take half of the 4 and half of the e squared. On the last set, we have negative 4 plus 2 natural log of 4. All right, combining like terms, I have 2 terms that are natural logs of 4. So the 2 natural log of 4 plus 2 natural log of 4 gives me 4 natural log of 4. So I should mark through what I've taken care of. I have a minus 1/2 4, which gives me minus 2 minus another 4, which gives me a minus 6. That takes care of those 2 terms. And then I have plus 1/2 e squared. Now the negative 3/2 and the negative 6 can combine to give me negative 7.5, or is it supposed to be? Yeah, that's correct. So that would be negative 7.5 plus 4 the natural log of 4 plus 1/2 e squared, whatever that comes out to be. It is a constant, all right? It is not it's not a variable expression because e is not a variable. E is a constant. So make sure that you remember that, all right? Does somebody want to multiply that out on their calculator and tell me what they get for it? We'll make note of it. Anybody get something? See what I got. I got about 1.74. All right, 1.74. And that would be in meters because it is displacement from where the total displacement, that's the total distance traveled, if you will. All right, so some of the distance traveled was backwards and forwards. And that accounted for the fact that the net displacement was about a -0.8. Okay, now we want to apply the net change theorem to this problem right here. We're going to work through an example using the net change theorem. So let's take a look at it. Oh, when we're looking at example 5, what it says is write an integral that expresses the increase in the perimeter of a square when its side length s increases from 2 units to 4 units, and evaluate the integral. So what does it mean by the increase in the perimeter? Well, let's suppose the perimeter was originally 10 and now the perimeter is 22. The increase then would be 12 because it went from 10 meters to 22 meters, which is an increase of 12 meters. So that's what we're looking for. But we're doing this with calculus, which can make it simpler to solve when we're talking about complicated formulas. These are not that complicated, but the method is the same when they are complicated. So the first thing you want to do is you want to write an expression which expresses the perimeter as a function of the side length that's changing. So this says the side length S increases from 2 units to 4 units. So S is what's changing. So we want to write the perimeter in terms of S. It is a square, which means that all the sides are the same. So I always find it helpful to have a picture and to go ahead and label the sides. And that tells me that the perimeter would be the sum of all 4 sides, or 4s. Now, in order to integrate, we have to have the derivative of the function for the integrand. So we take the derivative of 4s with respect to s. So this gives us the derivative with respect to s of 4s, which is equal to 4. And that means that p prime of s is 4. So again, we're taking the derivative of the perimeter function to serve as the integrand. And what we're going to do then is we're going to allow our limits of integration to represent the change in the side length s. So the side length s went from s equal 2 to s equal 4. So s changed from 2 to 4. And that's what gives us these limits of integration that you see right here. All right, that's the change in the variable. So we integrate the derivative of the perimeter with the changing limits of integration of side s. So coming down here, we get the integral from 2 to 4 of 4 ds. It's not a difficult integral as integrals go. It's one of the more straightforward ones. It's just a constant, which means that we get the variable 4s, and we evaluate between 2 and 4, which gives us 4 times 4 minus 2, which gives us 8. Now, what does this mean exactly? When we're looking at this, our original perimeter, like this, was 2, 2, 2, and 2. And now we're doubling each side so that each side is 4, 4, 4, and 4. On the first one, the perimeter would be 8. Does everybody see that? The perimeter would be 8. On the second square, the larger one, the perimeter is 16. The change in the perimeter is 8, which is 16 minus 8, which equals 8. And that 8 is that 8. So we're finding the net change in the perimeter by integrating over the change in the value of the side length, which is another way of thinking about the definite integral. Okay, let's take a look now at another example. This is example 6. We want to write an integral that quantifies the change in the area on the surface of a cube when its side length doubles from s units to 2 units, and evaluate the integral. Okay, so the first thing that we need to realize is that we have a cube. And a cube kind of, all sides are squares, right? Which means this is S, and this is S. And we want to talk about the surface area on this cube. So the first thing we need to do is we need to come up with a formula that relates the surface area to the variable that is changing. The change is occurring in the side length, which is going to double from S to 2S. But this time it doesn't give us a number. It just says it doubles. So our new one, of course, is going to be much larger, coming back like this. And this is 2S, 2S, and 2S. So our new cube is much larger. We want to know what is the net change in the surface area. So the first thing that we're going to do is we're going to write a formula for surface area, and we're going to look at the smaller cube. Remember that when you have a cube, and I'm looking for a cube, so my kingdom for a cube. I don't really have a cube. Do I have a cube? I'm looking around my office. About the best I can come up with is a Kleenex box, which is close to a cube, right? So when you're thinking about a Kleenex box, you've got two sides that have the top and the bottom, which is S squared. And then you've got the front side and the back side, that's S squared. And then you've got the left side and you've got the right side, and that's S squared. So you basically have 1, 2, 3, 4, 5, 6 sides that all have area S squared. So the surface area formula is 6 times S squared. Now we want to take the derivative of that in order to have an integrand. So we're integrating the derivative of that. So we take the derivative of surface area with respect to S, which gives us 12S. Now we want to write our integral, but the problem is in our integral, the change in the side length is not a number. The change in the side length is going from S to 2S. So because we have S in the limits of integration, we want to use a different variable in the integrand, a dummy variable. So instead of using S, use T instead. So this is going to become 12T dt. Remember that the variable that you use back here is a dummy variable. It helps you to do the antiderivative, but once you plug in the limits of integration, that dummy variable disappears from the problem and is gone forever. And we just don't want to have S's on the limits of integration and S's in here. That gets too confusing. All right, so we're going to leave S for the limits of integration and change this to anything else you want other than S. Now, the next thing that we're going to do is we're going to go ahead and integrate that side. So when we integrate S to 2S of 12T dt, We apply the power rule. So we have 12 t to the 1 plus 1 divided by that, which is 2, evaluated between s and 2s. So this is 6t squared evaluated between s and 2s. So we're going to replace the t with the limits of integration and then subtract the upper minus the lower. So this gives me 6 times, and then I have 2s quantity squared minus s squared, which gives me 6 times 4s squared minus s squared, which gives me 6 times 3s squared, which gives me 18s squared. That means that the change in the surface area is 18s squared units. And if you're wondering if that's actually accurate, we can look back at our original 2 pictures here and realize that on this larger cube, each individual side, there are 6 of them, and each individual side has area of 4s squared. Because you multiply 2s by 2s, you get 4s squared, and that gives us 24s squared. The difference between 24s squared and 6s squared, what you see here and what you see here, is 18s squared. So that's the net change in the surface area when you double the side length. Okay, any questions over that? Okay, we have one more small little bit to do out of this section, which is unrelated to net change. This is a
I do
complete
have a
change of
question.
topic. Oh, you do have a question. Go ahead, Juan.
Yeah. So why did we plug in 4s and not 18s squared? I got lost there.
Here I'm just computing what the surface area is of this larger cube.
Oh, okay. Now I
So
see.
that would be 4s squared. Each side here is 4s squared of area. And the net change between the two is 18s squared.
Oh, okay. So that's why that's the way we.
And
like,
that's why
prove
we
it.
got 18.
Okay, perfect.
Okay,
That's all. Thanks.
sure. All right, let's look at this last little bit, which is unrelated to net change. It's some formulas that help us to compute the definite integral of even and odd functions. So I want to remind you what an even and an odd function is so that you can kind of, well, so you know what you're doing, right? If you don't know what an even and odd function is, then you're not going to be able to apply these new rules. So an even function is like x squared, and it has the property that f of negative x equals f of x for all the x in the domain. Okay, now this is actually an odd graph, so let's look at an even one. So here's an even one right here. Here's x squared. What does that mean? Well, if I take 1 and square it, I get 1. If I take negative 1 and square it, I still get 1. That's even. Even, in other words, is what we call y-axis symmetric. So these are even functions, and that means that they are y-axis symmetric. And the way to know that they're even is to replace x with negative x and see that you get the same y value as if you had not replaced x with negative x. If you replace x with negative x and you get the same thing, it is an even function. Cosine of x, which is here in blue, is also an even function. You can tell because it folds on the y-axis. If you make the y-axis the crease of the paper, the two parts will lay together perfectly. So that's an even function. What about an odd function? this is an example of an odd function. An odd function is also called an origin symmetric function. And that means that it has to fold twice. So this is a double fold, once on the x-axis, once on the y-axis. So it has to fold 2 times. This time when you replace x with negative x, you get not the same y value, but the same number, but with opposite sign. So you do have a relationship. It's just that when you change the sign of the x, instead of getting the same y value, you get its opposite. So for example, on the graph, if I plug in 1 into x cubed, I get out 1. If I plug in -1 to x cubed, I don't get 1, I get -1. Same magnitude, opposite sign. Now, how are they symmetric? They're symmetric across the origin, and that if I fold it 2 times, once on the x-axis and then once on the y-axis, the 2 parts will lay together. So if you can visualize on this first fold, it looks like this. And then on the second fold, that dotted part will lay on top of the purple and it will match up. So x cubed is the most commonly thought of odd function. In fact, that's where it gets its name. All odd power functions are odd. And then sine of x, which is here in blue, is also an odd function. So now that I've reminded you of what even and odd means, let's look at the rules that make integration a little bit simpler. Now, a caveat for you guys. Yes, it does make your life simpler. Can you live without these rules and still do well? Yes, you can. You can live without these rules and still get 100%. It's just a little more work. That's all. All right. So these are to make your life easier, but they're not strictly necessary. So what does it mean? When we're looking at continuous functions, such that we have an even function, f of -x equals f of x. So in other words, an even function. And we're integrating from -a to a of f of x dx, then we could double it and just go from 0 to a. Now, what do we mean by -a to a? Let's suppose that we're going from -5 to 5 on x to the 4th dx, which is definitely an even function because it's a power function with an even power. If I go from -5 to 5, what they're saying is that its y-axis symmetric. It's exactly the same graph on both sides of the y-axis. So I've got the same amount of area on this side as I have on this side. And since I have the same amount of area on both sides of the graph, I could integrate half of the graph and double it. So what they're saying then is I could instead double the area and go from 0 to 5 of x to the 4th dx. Now, why is that an advantage? Because having a limit of integration of 0 is the easiest number to substitute in for a limit of integration because it just wipes the variable out, right? So 0 is the easiest number to plug in. So instead of integrating from -5 to 5, I integrate from 0 to 5 and then I double the area. All right. And again, let's take a look up here at our graph. So on this graph, let's suppose that we're graphing, what is this, cosine? So this value right here is -pi/2, and this value is pi/2. So if I wanted to integrate from -pi/2 to pi/2 of cosine of x dx, I could instead integrate from 0 to pi/2 and double the area. Because the area under the curve is the same. Does everybody see that? I don't know if I can get all of it colored in. And this area right here is exactly half of the total area. So I could just find half the area and then I could double it, right? Multiply it by 2, all right? And that would give me both both sides of the purple, okay? So this one is doing the yellow times 2, and this is doing the purple, right? So when you're doing the purple, you're integrating from here all the way to here. When you're doing the yellow, you're integrating from 0 to pi over 2, but then you're doubling how much you have, which gives you the same area. Okay. Let's take a look at this one right here. Here's a graph of an even function. I know it's an even function because it's y-axis symmetric. So I could integrate from -3 to 3, or I could integrate from 0 to 3 and double it. Could I integrate from -3 to 0 and double that? Yes, I could. It's the same amount of area. So regardless of which one I did, it would be the same. So integrating from -3 to 3 of f of x dx would be the same as integrating from -3 to 0 of f of x dx and doubling it, or integrating from 0 to 3 of f of x dx and doubling that. All right, be the same. Okay. It does make your life a little bit easier, but of course you have to recognize when you have an even symmetric graph, which pretty much the only even symmetric ones I have memorized are cosine and the even power functions. Now, what about the other rule? The other rule is for odd functions. So when we're looking at this one right here, we're talking about odd functions. This says if I'm integrating from -a to a of an odd function, so let's say we're going from -5 to 5 of x to the 5th dx. It says don't even bother because it's 0. Now this one is truly handy, all right? This is really handy because then I don't have to do any work at all. I just know it's 0. Why would it be 0? Well, let's scroll down and look at the picture. If you're looking at a picture like this one here, this is an origin symmetric or an odd symmetric function. So this one is odd. My pen is not writing. So we have an odd function. And if you look at it, because it is origin symmetric, part of the graph is above and part of the graph is below. It wouldn't be origin symmetric if it's not, because you have to double fold. You've got to fold twice. So it's required that part be above and part be below the axis. And because that, you've got positive area above the axis and positive area below the axis, or negative area below the axis, not positive, negative. So the fact that it is symmetric, that they lay exactly on top of each other, means that I have exactly the amount of positive area here as I have negative area here. Because when I fold it twice, they have to line up exactly, which means that this area might come out to be a positive 7, and this area then would have to be a negative 7. And so 7 minus 7 gives you 0. So there's 0 net area. All right, so the net area is 0. So this says if you have an odd function like sine or x to an odd power, then you know that the area between a symmetric limit of integration is going to be 0. Now, does this apply to something like -3 to 2 of f of x dx? Does it apply to that one? No, it does not. These numbers right here have to be opposites. So it would not apply on this one. All right. we have, I think,
But question, in that
Yep.
case, we could say that it has to be a negative area, a result.
well, what we could do, what we could do on this one is we could say, let's say this is from -3 to 2 of f of x dx, and this is an odd function. We could say this is the integral from -3 to -2 of f of x dx, plus the integral from -2 to 2 of f of x dx. Now, why would I want to write it like that?
Because it'll equal 0, the other one, and then
Yes,
you'll just have to
this
find.
one, because the limits of integration are opposites and it's an odd function, that one will go to 0, which just leaves me this one left to compute. That's it. All right.
Yeah.
Okay. We have 2 small examples left to do, and then we're going to move on to section 5.5. So looking at this one, example 7, we have the integral from -2 to 2 of x to the 4th dx. This is a power function. Power is even. And because it's a power is even, it's an even function, which means that the integral from -2 to 2 is the same as the integral from 0 to 2 of x to the 4th dx doubled. So then I simply apply the rule. 4 plus 1 gives me 5. Divide by the new power of 5. Multiply that result by 2 and integrate from 0 to 2. And that would give me 2/5 times 2 to the 5th minus 0 to the 5th. The advantage with 0 is that it goes to 0. 2 to the 5th is 32, and this would actually end up giving me 64/5, right, as the result. Now let's look at the second one. The second one, to my mind, is the more difficult one to detect. But the way to detect it is to note that this is the sum of 2 terms, and both of the terms are power functions, x raised to a power, and the power is odd in both cases. And since the power is odd in both cases, you must have that f of -x is equal to negative f of x. And this means that it comes to 0. One of the things that I said I was going to point out to you today was the integral tables. In the front and back cover of most calculus books, it has integration tables. Your textbook also has an integration table. I believe it's at the back. But I don't like the one in our textbook because it's in X form, not U form. You want the one with the chain rule built into it. And that's what this one is. Now you can tell that there are, I think, 100 and how many are there? 50, about 150 different problems. So there are a lot of different integrals that are on this page. Now you can find integral tables on the internet if you Google them. I would, however, always Google integration tables U form. That's the form that's most easy to use. So when you look at these, and I'm going to zoom in, hopefully it'll show up well enough. You can see that it has all of the various integration tables that you might be wanting to use. All right. So these are ones that give you the formulas that we are learning to derive right now and that you'll be working on in Calculus 2. When we get into section 5.7, we'll be using tables of formulas that come out of this section. It will in fact be these 3 right here: arcsine, arctangent, and arcsecant. And I'll go through how to use the formula that's here in the table and to convert it into the antiderivative that you see on the right. So what you have is the integral in some form on the left and the antiderivative on the right. It's your job to make the original problem totally match the form on the left before you can use the antiderivative form on the right. And I go through that in detail when we cover section 5.7. We've now completed the net change theorem, and we want to switch gears and focus on U substitution integration. This is how we will deal with composition, which is occurring inside the integrand.